This is part 2 of the thermodynamics chapter. So we were talking about endothermic and exothermic reactions a few minutes ago. And with endothermic reactions, and we've looked at this energy diagram in the past, but let's just revisit that. Remember, this line represents the energy of your reactants. This line represents the energy of your products. Now remember, the amount of energy that has to be obtained in order for reactants to actually form products is called the activation energy. So when you come up here to get the very top, we call this the energy of activation. This is the amount of energy, the difference between here, the reactants, where they start, and the top of the hill. And then once you've reached the activation energy, you have your activated complex, and then finally the products can start to form. And then when the energy levels off, that represents the energy of the products that the products possess. So the difference between the energy of the reactants and the top of the hill, again, is called the activation energy. But the difference between where the products level off and where the reactant started, which represents here, is called the delta H, or the change in enthalpy. Now this is a positive delta H because overall the energy of the products increased in reference to where the reactants began. This is an energy diagram for an endothermic reaction. An exothermic reaction would look similar as far as that goes. However, man, this thing's going crazy. However, you still have your activation energy here, but notice the energy of the products ends up at a lower energy than the reactants. So if overall the net energy change is the reactants have a higher energy than the products, this will be called an exothermic reaction, and so it would have a negative delta H. Now remember, the enthalpy is the heat content of the system. So in this case, exothermic, and in the previous diagram, it was endothermic. So let's look at how we would construct a thermochemical equation. All right, so here's the chemical reaction that similar to one we've looked at in the past. We have 2 magnesiums plus oxygen gas reacting and forming 2 magnesium oxides. And you're told here that the delta H is a negative 1,204 kilojoules. Notice since it's negative, okay, we can answer part A, is the reaction endothermic or exothermic? Well, since we have a negative sign here, we know that it's exothermic, because if your delta H is negative, that indicates that the energy of the products is less than the energy of the reactants. So negative is because that's a negative enthalpy. Okay. Now, the next part of this says draw a complete enthalpy diagram for this reaction. So when you're drawing an enthalpy diagram, if you think back to the 2 graphs we just looked at, basically on the enthalpy diagrams, you're not including the activation energy, but you have a line that represents the energy of your reactants and a line that represents the energy of your products. So what you want to do is you want to draw, I'm going to try to make that as straight as I can, 2 lines that are parallel to each other on your graph. And so this represents energy increasing as you go up, and this just represents the reaction coordinate. So if the reaction is exothermic, which we have here, then you're going to put an arrow pointing down, and this arrow represents the direction the energy is flowing, so the energy is lowering. And so you would put here that delta H is 1,204 kilojoules, and the direction indicates it's lowering energy. Since this is releasing energy, you're going to put the products on this line. So the products that formed were the 2 magnesium oxides. And then this line represents the energy of your reactants for this example, because since it's exothermic, the reactants have a higher energy. So here you put the formula for your reactants. So 2 magnesiums plus O2. So this will be a thermochemical enthalpy diagram for this thermochemical equation. So you got to decide if it's exothermic. That means you're going to point the arrow down. The line at the bottom then would represent your products. The line at the top represents the energy of the reactants. So notice the energy of the reactants is higher than the energy of the products since this is exothermic. And the overall enthalpy change was 1,204 kilojoules, and it released it. So it released that amount of energy through the process. Now, if this had been an endothermic process, if this had been positive, you would have had the arrow pointing up for your delta H. You would have put the products on the top, and you would have put the reactants on the bottom line. Again, because that would be the reactant energy would be lower than the product energy. But this was exothermic, so we don't worry about that. Calorimetry is the next section. Calorimetry is a way that we determine the amount of heat absorbed or released during a physical change or a chemical change, and we measure it with a device known as a calorimeter. Usually, we do this by looking at the change in temperature of a known quantity of water. 1 calorie is defined as the heat that's required to raise the temperature of 1 gram of water by 1 degree Celsius. Now, the unit of energy that we use is the joule, and sometimes you see kilojoules. This is our SI unit of heat. This is our modern unit that we use in thermochemistry. A joule is equivalent to 1 Newton meter, or if you break that down even further, 1 kilogram times meter squared per second squared. If you remember that, that was from the Eqns equation, the root mean square velocity equation from the gases chapter. 1 joule is also equal to 4.184 calories. This is an example of a calorimeter, like the inside workings of it. You would have your reaction chamber here. You put your reactants here. This is called the ignition coil, where you would heat it and it would combust the reactants. You have a stirrer that keeps the water stirred up here. It's surrounded by water, of course, a thermometer here. It is insulated as well. So you would combust this and you would measure if it released heat or if it absorbed heat. This would be your system, and then the water would be the surroundings here. You can make a cheaper kind of calorimeter by using 2 styrofoam cups nested inside of each other, and you could put your reaction in the water, put a heated piece of metal, or even actual reaction. You can measure dissolving of a substance and still get the same result. And of course, your specific heat values that you would be using, you would read those off of a chart. And we will look at some of these calculations later. The formula that we will use for solving for specific heat is more commonly known as Q equals MCAT, or Q equals MC delta T. And we're going to pick up here in our next lesson.